welcome to our demo presentation, Opening the Black Box, explaining learned cost models for databases. Learned cost models are designed to predict query execution costs in databases, like the query runtime. These models learn from previous query execution costs to estimate costs for unseen queries. For this, they make typically use of neural networks as they can learn arbitrary complex functions. That way, learned cost models are able to come up with better predictions that are more accurate than traditional approaches. Still, there unfortunately remain queries where a learned cost model misestimates the query execution costs significantly. So to fix and improve now our cost model, we need to know why it mispredicts the query execution costs. However, we unfortunately cannot really debug the model and trace the error down. The reason is that the model relies on neural networks that behave as a black box in their prediction. In this demonstration, we now want to open this black box and achieve debuggability for learned cost models. Our main idea is to make learned cost models explainable by showing how and why they came to their predictions. This helps us to understand if and where the model relied on false assumptions. So the main information that the learned cost model learns from is the physical query plan. Here, every node typically contributes to the overall prediction of the runtime. In our demonstration, we propose to identify those nodes in the query plan that were most important during the prediction. For this, we propose to leverage explainability algorithms to provide an importance score for each node in the plan that reflects how important it was during the prediction. Overall, this information gives insights in what the model has learned about the nodes and how it reasons about the query plan. And this helps in the end to make the model explainable, as I will show now. At first, the scores allows us to obtain a node ranking that shows the most important nodes for the prediction. Moreover, we can analyze the correlation between the actual runtime fraction in the query plan and the importance scores. These both ways help to identify false assumptions and make mistakes in the knowledge of the model. This in turn helps to improve future learned cost models. Additionally, we report various metrics to assess the quality of the explanations. In our demonstration, we use the zero-shot cost model and modify and apply 3 different explainers from the literature, and additionally propose a new explainer, which is called a diff mask. Let me now walk you to our demo. Our demo comes as an interactive web page. Here you can select first the dataset for further evaluation, like DBCH, baseball, or MDB. Once this is selected, you can also select a workload, which is basically a selection of queries. Moreover, you can also select a certain model that is trained on a set of datasets. Now a table shows up with different columns that describe our workload. Here, each query has an ID, the actual runtime, the number of operators, and more metadata. Once you select a query, more information is displayed. At the top, you can see the sequence string. It indicates the query with one table and some filter attributes. The query graph is shown in the center. In this demo, we use the zero-shot cost estimation model that uses different node types in the query graph, such as physical operators in gray or table nodes in blue. If you click on such a node, more information is shown above, like cardinality estimates. At the top right, we can see the actual runtime of 0.8 seconds and the predicted runtime of 0.3 seconds, which results in a Q error of 2.32, which is actually bad. So now we want to explain the prediction and see why the cost model came to this prediction. For this, we select first an explainer, like for instance, diff mask. At first, we get a list of nodes that were most important for the prediction. If we change here now the graph mode, we can see the node importance in the colored scale that highlights the most important operators. By changing the mode, we can compare the scores with the actual operator runtimes and see differences in the explanations. Interestingly, according to the explainer, the aggregations were highly important during the prediction, while in reality, the scan had the longest runtime. We can make this comparison even more simple by analyzing the correlations between the actual runtime and the node importance, where we again see a mismatch of the node importance and the actual node runtime. They are here shown as a fraction of 1. Finally, we want to know if our explanation is reliable. For this, we can inspect fidelity and characterization score that indicate a good quality of our explanation. Overall, we believe that our insights help to improve future cost models by paving the road for debuggability.